Okay, now we want to talk about what happens to large stars. So I've got summarized here what we've already talked about. Very small objects cannot convert hydrogen into helium. So we're going to refer to these things as brown dwarfs, BDs, and they're going to turn into black dwarfs, BDs. So brown dwarfs turn into black dwarfs as they eventually cool off to absolute zero. And then small stars, okay, smaller than our sun, will be able to convert hydrogen into helium, but that's it. And so these are going to be red dwarfs, and eventually they're going to cool off and turn into black dwarfs. Then we've talked about the medium-sized star, which includes our sun. So these objects are going to be able to convert hydrogen into helium. They are going to be able to convert the helium into carbon. Now, depending on their size, they will be able to make elements all the way up to silicon. So as the core collapses, the outer part expands, becomes the red giant. Okay, then as the star dies, the red giant part is jettisoned as the planetary nebula, and what's left over in the middle is going to be the core. That's the white dwarf, and then the white dwarf is going to cool off and turn into the black dwarf. So far, nothing really too different is happening here. So now we want to go to the large stars and find out what happens to them. So these are going to be between 8 times the size of our sun, or 8 times the mass of our sun, up to 30 times the mass of our sun. They're going to ignite. They're going to convert hydrogen to helium. As it starts to run out of hydrogen, it's going to turn into a giant. Then as it's going to start to make carbon from the helium. Eventually it's going to start to run out of helium. The core is going to collapse a little bit more. It's going to get hotter. The outer part's going to expand a little bit more. And by the time it's up here to silicon, okay, now we have what's referred to as a blue supergiant. So the outer part of this object is the same as the diameter of the orbit of Pluto. So these things are huge. But this time, as the core continues to collapse because of gravity, the temperature is going to get hot enough that silicon will be able to be fused and turned into iron. Now this is a very, very bad thing, because we found out that with iron, if you take iron and you pull it apart, nothing's going to happen. So if it undergoes nuclear fission and you pull it apart, it does not release any energy. If you take 2 irons and you smash them together, that's nuclear fusion, again, no energy is released from that. So this is really bad, because the energy of the nuclear explosion was providing the thermal gas pressure, which was pushing outwards and keeping this object from collapsing. So now this object is really going to start to collapse. Now the nucleus is going to have one remaining thing that it can do, and it has to do with the inside of the core of this object is now going to be composed of iron nucleuses. Okay, so we can look up on the periodic table and we can find iron. And so we can look at how many protons are in its nucleus, and we can estimate how many neutrons are in its nucleus. But the point is, there's both protons and neutrons in its nucleus. So let's draw a picture of the nucleus of this thing. It's going to consist of a whole bunch of iron nucleuses, and each one of them is going to have a certain number of neutrons, and they're going to have a certain number of protons. Now, there is a little bit of energy still in each one of these iron nucleuses, and it has to do with electricity. So you should know that opposites attract. So a positively charged particle and a negatively charged particle would attract each other according to the force of electricity. But if you have two charges that are the same, they repel. So a positive charge and a positive charge would repel each other. So inside the nucleuses of all of these nucleuses in the core of this object, there are both protons and neutrons, and the protons are pushing against each other. So what would happen if each of these protons was to turn into a neutron? So now we know that neutrons, they have no electrical charge, okay? So now there's no longer any electrical force pushing outwards inside of these nucleuses. And so gravity is going to pull it in. So it's as if I take this pen, as long as there is this electrical energy, then this pen is being held up. It's pushing against the earth down here. But as soon as the electrical force goes away, now this thing is going to fall and it's going to generate energy. So it's going to change from potential energy to kinetic energy as it falls inward, and that's going to produce a gigantic explosion. And that gigantic explosion, which we call a supernova, is going to blast the outer layers, so the blue supergiant, so all of those layers are going to be blasted away in this colossal explosion. Okay, so to give you an idea for why do the layers, why do they go off into outer space at such a high rate, I want you to watch this video here. Okay, if you can't find that video, go to the internet and look for Physics Girl, and then type in Physics Girl supernova. Okay, did you watch the video? So pretty interesting. So what's happening is that according to the weak nuclear force, a proton can change into a neutron. So protons can change into neutrons, neutrons can change into protons. So that's called the weak nuclear force when that happens. And so that force is going to change all of the protons, or most of them, inside the iron nucleuses, inside the core, into neutrons, and then the core is going to collapse. And then as the outer layers, the blue giant part of it, hit that solid core, they're going to bounce back into outer space as the supernova. So I wanted you also to take a look at the bottom of the slide here. It talks about just how powerful supernovas are and how many joules of energy that they release. And so a supernova releases as much energy in 1 second as does an entire galaxy of stars produce in 1 second. And they're so bright that you can see a supernova occurring in our galaxy, or you can even see a supernova occurring in nearby galaxies. So they're incredibly bright. Okay, so what is the thing remaining after the supernova has occurred? So this thing is going to be called a neutron star. And it's going to be composed of neutrons. It's going to have a diameter of about 16 kilometers. So imagine a star. You know how big a star is. It's going to collapse down to the size of the city of Springfield, Missouri, 16 kilometers. It's going to have a density as though you had taken 185 Great Pyramids of Egypt, crushed them down, and stick them inside of a teaspoon. So that's going to be the density. The density is so great that if you were to step foot onto the surface of this object, you would be squished until you were 1 atom thick, spread out on the surface of this object. So that's what a neutron star is going to be. So to give you an idea for how big this stuff is, imagine that our sun is 1.5 meters in diameter, about 4.5 feet. Okay, then Jupiter, in comparison, is going to be the size of a basketball. Earth is going to be the size of a marble. So that when a star turns into a white dwarf, that is going to be the size of the Earth. So imagine an object that used to be 4.5 feet in diameter, and now it's the size of a marble. Okay, when it turns into a neutron star, it's going to be the size of the head of a pin in comparison to that original object, which was 1.5 meters in diameter. All right, now what is keeping gravity at bay? So it was, for all of this stuff up here, it was electron degeneracy pressure. So when something turns into a black dwarf, black dwarf, black dwarf, gravity is being kept at bay by the electron degeneracy pressure. What is keeping gravity at bay with the neutron star? So let's go and take a look at this. And it turns out that inside the nucleus of every atom is another apartment building. So you had the electron apartment building, the atomic hotel, was where the electrons lived in their energy levels. Well, inside the nucleus of every atom is a nuclear apartment building. According to the laws of quantum mechanics, the protons and neutrons live on energy levels inside the nucleus, the same way that the electrons live in energy levels inside the atom. And according to the rules of quantum mechanics, only a certain number of protons and neutrons can live on the first floor, and a certain number can live on the second floor and the third floor, and so forth. So imagine that you've got two nucleuses that are getting closer and closer together. So what would happen is that maybe a proton or a neutron on this nucleus might look at this one over here and say, I think I'm going to jump and live on a lower energy level on this nucleus. And then this nucleus is going to say, oh no, you don't. Because according to the laws of quantum mechanics, there's only a certain number of protons and neutrons that can live on each of the energy levels. So this is going to put a limit on how close nuclei can get to each other. And so we're going to call this the neutron degeneracy pressure. So that's what's going to keep neutron stars from collapsing. Okay, let's take a break. And when we come back, we're going to talk about a special kind of neutron star called a pulsar. We'll be back in just a moment.